Hi students, please welcome to the Physics Wala channel. Yes, in UMEED NEET English batch, in today's session we are going to discuss a very important chapter, not so much important compared to your board examinations. Okay, anyway, let's see what is the chapter. Electrostatic potential and capacitance. Potential and capacitance. Okay, so what are the important topics what we have to learn, and what are the models, and what are the previous years questions they have given from this chapter in your NEET examinations, and everything we will discuss in this present video, in this video. Okay, so before going to discuss the important point, that is synopsis and the numericals, okay, let us have the weightage of this particular chapter. Whenever we go with the weightage, as I said in the last video, from the two chapters, the first two chapters of the 12th standard NCRT, that is electric charges and fields, electric potential and capacitance. So you can expect two to three questions for your NEET entrance examinations. Okay, but on an average, that is in some of the years, two questions can be asked in only from the first chapter. In some of the years, the two questions can be asked in the second chapter, that is in electrostatic potential and capacitance. Overall, we can say on an average you can expect two questions from this particular chapter, electrostatic potential and capacitance. Okay, so let us see what are the important points, that is a synopsis, and important models, that is MCQs, and we will cover PYQ, that is what are the questions which are asked in the previous year's NEET paper from the past 10 to 15 years analysis, and I request you to prepare each and every formula or each and every concept what we are discussing in this video. Okay, it is more sufficient. Happily you can score a very good marks from this. You can answer all the questions, maximum to maximum all the questions coming from this particular chapter. Okay, so if you prepare and if you practice as many times as possible, the formulas are very important. If you don't know the formulas, and if you don't know the meaning of the symbols in each and every formula, you can't answer those questions. Okay, so please be concentrated and please prepare well, and if you have any doubt, you please comment so that I will go through that. So let us move on to the important points. So here, especially whenever we come to this electrostatic potential capacitance, majorly we have to discuss the two important things, that is electrostatic potential energy, and the work done, and what is the dipole potential energy, and what is the polar or non-polar dielectrics, and what is the effect of dielectric. Okay, and later we will go with the capacitor, the combination of capacitor, what is the energy stored in the capacitor, and what are the important things, how to find out the common potential, and to how to find out the individual potential difference across each and every capacitor in series combination, and what is the charges stored in individual capacitor in a parallel combination, all those things. Okay, let us learn in detail one by one. First of all, let us concentrate on electrostatic potential here. So whenever we go with electrostatic potential, we can say it is nothing but the work done. It is nothing but the work done denoted by capital V. The work done to bring a charge from infinity to a point inside the field, is it there? So V is called as electrostatic potential. V is the electrostatic potential, and W is nothing but the work done to bring a charge. So please see here, what is a Q naught? Q naught is the charge moved from one point to another point, that is especially from infinity to a point inside the field. What is the meaning of infinity in physics? Infinity says that wherever the point is outside the field, then that point is taken as a infinite point. Okay, from this we have to understand that W is equals to Q naught into V. Q naught into, it is a basic idea we have to keep in our mind. Okay, so please make sure you are understanding each and every point, ma. And later, what is the potential difference here? What is the electrostatic potential difference? What is electrostatic potential difference? So see here, How can we define this? How can we give the definition for this? Whenever there is a source charge, let us say capital Q, let us say this is the electrostatic field, electric field. Let us say there are 2 points A and there is a another point B. A and B are the 2 points. Suppose if you want to bring a charge Q naught from A to B, we can say that, see here, finally VB minus VA will give you the potential difference. What is VB? Potential of the point A. VA is the potential of the point A. So it is equals to the work done divided by the charge moved. This is the potential difference. Is it clear? So simply we can say the amount of work done to move a charge from one point to another point inside a field. Is said to be electrostatic potential difference. Therefore, the work done to move a charge from one point to another point, is written as VB minus VA. VA. Okay, and here it should be very clear. That so final potential minus initial potential. Initial potential is a very important. So Q naught is the test charge moved from one point to another point. Suppose if the charge is moved from B to the point A, then the potential difference will become equals to VA minus VB. Is it clear? So like that, we have to understand about this. The work done to move a charge from one point to another point inside a field. Okay. Later, we have to understand what is the electrostatic potential. Due to a point charge. Okay, so what is the electrostatic potential due to a point charge here? Let us say Q is a charge and let P be a point which is at a distance of R from the source charge. Therefore, electrostatic potential is equals to 1 by 4 pi epsilon naught into Q divided by R. What is 1 by 4 pi epsilon naught value? We can say it is 9 into 10 to the power of 9. 10 to the power of 9. We can say Newton meter square per coulomb square. Is it clear? So that is about the value of 1 by 4 pi epsilon naught. From this we can say that electrostatic potential due to a point charge is inversely proportional to the distance. That means as we move away from the source charge, the electric potential gradually decreases. So whenever you plot a graph, by taking the distance along the x-axis and electrostatic potential along the y-axis, then it will be a rectangular hyperbola, that is a non-linear curve as shown in the figure. Okay, so that is a electrostatic potential due to a point charge. Now let us see potential. What is the potential due to system of charges? Potential due to system of charges. Okay. So how can we understand? The potential due to system of charge? Let us say there are the system of charges. Let us say having Q1, Q2, Q3, and so on Qn. So net potential at some point P, which is located at a distance of R1 from the first charge, R2 from the second charge, and R3 from the third charge, Rn from the nth charge. Then the net potential at the point P is always be equals to 1 by 4 pi epsilon naught into, we can say, Q1 plus or minus Q2 plus or minus so on Qn divided by, what is the value of this? Okay, I will rewrite this. Sorry, I will write this value. Observe this. We can say Q1 by R1 plus or minus Q2 by R2 plus or minus so on Qn divided by Rn. Or simply we can say that net potential of the point B due to system of charges will be equals to 1 by 4 pi epsilon naught into sigma Qi divided by Ri, where I is equals to 1 to n. Okay, so if the charge is positive, then we will take the potential as positive. If the charge is negative, then we will take the potential as a negative. Is it clear? So there is a thing we have to keep in our mind. Later we have to understand that electrostatic potential is a scalar physical quantity. Is a scalar physical quantity. Now, what is the SI unit of this here? SI unit is we can say that volt. We can say it is a volt. Volt is the SI unit of electrostatic potential. So what is the, we can say, dimensional formula for electrostatic potential? We can say work done by charge, no, m power 1 L power 2 T power minus 2 divided by charge is a power 1 T power minus 1. If you do simplification, we can say m power 1 L power 2 T power minus 1 a to the power of minus 1. Is it? This is the dimensional formula for electrostatic potential or electrical potential. Okay. So like that we have to think about the point here, and later we have to understand what is the potential. What is the potential due to? What is the potential due to? What is that? We can say due to the simple system we call it as a dipole. Due to a dipole, due to a dipole, potential due to a dipole. So see here, whenever we consider a dipole, let us say this is a minus q charge and this is a plus q charge here. Let us say this is a minus q and this is a plus q, which is, let O be the center of a dipole. If P is a point which is making an angle, the line joining the point P and the center of the dipole, is making an angle theta with the dipole moment. Then we can say what is the potential at the point P due to dipole? It is equals to 1 by 4 pi epsilon naught into, we can say, P cos theta divided by r square, or in vector form. How can we write this? So v at the point P is equals to 1 by 4 pi epsilon naught into, we can say that P vector dot r cap divided by r square. Is it clear? So I hope you understood this point clearly. What is the P? P is called as dipole moment, where P is equals to Q into 2A, and we can call this as dipole moment. Is it clear? I hope you are understanding each and every point here. That is electrostatic potential due to a point charge and due to a system of charges and due to a dipole at any point. What is the theta? Theta is the angle made by the line joining the point P and the center of the dipole with the dipole moment. Okay. And later we have to understand. So see here, potential due to dipole. Whenever you observe the equation carefully here, potential due to dipole is inversely proportional to the square of the distance. So whenever you plot the graph by taking the distance along the x-axis and the potential along the y-axis, then again it will be a rectangular hyperbola as shown in the figure. Okay. I hope you understood this question clearly. Now let us move on to the next thing. What is the next thing we can say? See here. Consider the two spheres. Consider two spheres having the radius r1, and initially it has given a charge. Let us say q1. Initially it has given a charge q1, and let's say whenever we consider another charge of radius, let it be r2, and a charge of q2 is given to it. Is it clear? Now observe, this is the initial case. So what is the potential of the first one? We can say first sphere is 1 by 4 pi epsilon naught into q1 divided by r1, and potential due to second sphere is 1 by 4 pi epsilon naught into q2 divided by r2. Is it clear? Now in the second case, let us say this is the first case. And when the two spheres are connected, are connected, when the two spheres are connected, by a metallic wire, by a conducting wire or a metallic wire. It may be a conducting wire or a metallic wire. Then we can say that see here, both the spheres will share their charges. Both the spheres will share their charges until their potential becomes same. Until their potential will become same, or until they attain the same potential. From this we can say that q1 by r1 is equals to q2 divided by r2. So from this, so please think about this. q2 can be written as r2 divided by r1 into q1. So what is the new charge? What is the new charge we can say? New charge. How can you get what is the, let us say, q1 dash and q2 dash are the new charges. q1 dash and q2 dash are the new charges on both the spheres, So how can we do this? Just apply law of conservation of charge. What is the law of conservation of charge? Says if capital Q is nothing but q1 plus q2, which is nothing but q1 dash plus q2 dash. So just apply. What is capital Q? Capital Q is nothing but the total initial charge, on the system. Is it clear? Capital Q is the total initial charge on the system. According to law of conservation of charge can neither be created nor be destroyed. So charge on an isolated body always remains constant. Therefore, Q can be written as q1 plus q2. So just substitute the value of this value here. So q2 is equals to r2 divided by r1 into q1. Okay, so just do substitution and simplification. Then we can say that the new charge can be written as q1 dash can be written as q into r1 divided by r1 plus r2. Is it clear? So please think about this. What is q1? q2 is equals to r2 by r1 into q1. We take q1 as a common factor, then we can do r1 into q. So like that we have to think about these things here. I hope you understood this point clearly. And similarly, q2 dash becomes equals to q into r2 divided by r1 plus r2. Is it clear? So this is how we can get the new charge on both the spheres after connecting by a metallic wire or a conducting wire. Okay, so please make sure you are understanding how to approach and how to analyze these things things. Okay, so let us move on to the next one. Okay, if you get confusion, we can say q1 dash, q2 dash, and q2 dash into the q1 dash. So now you can substitute, then you will get that formula. So please remember this as a shortcut to find the new charges when both the spheres are connected by a conducting wire. Okay. So let us move on to the next concept. That is, what is the potential energy? What is the potential energy? So please make sure about this. See, observe this. Potential energy usually denoted by capital letter U. Potential energy is nothing but work done. It is nothing but the work done to move a charge, or to bring a charge from infinity to a point inside the field, That is nothing but work done. Is it clear? And work done can be written as potential difference into charge, or we can say simply potential into charge moved. Okay, and please observe this. Potential energy is always defined for system. We cannot define the potential energy for a single charge. We cannot give any potential or potential energy definition. It is always defined for a system of charges. For simplest system, so see here, in case of two charges, let us say Q1 is one charge and Q2 is another charge. They are separated by a distance, let it be R12 or R21. Anyway, we can say. We can write. Therefore, what is the potential energy for system of two charges? We can say 1 by 4 pi epsilon naught into Q1 Q2 divided by R21 or R12, or simply we can say R. Simply we can say R. This is the expression for potential energy for system of two charges. For system of two charges. Okay. I hope you understood this question, understood this point clearly. Now, similarly, whenever we move on to the in case of the three charges, in case of three charges, let us say Q1 is one charge, Q2 is another charge, Q3 is another charge, and the distance of separation, let us say R12, and this is R23, and this is R31 or R13. Then the potential energy can be written as 1 by 4 pi epsilon naught into, we can say see here, Q1 Q2 divided by R12 plus Q2 Q3 divided by R23 plus Q3 Q1 divided by R31. This is the expression for potential energy for system of three charges, as shown in the figure. So based on this expression, we can have, or we can expect one type of question. What is that? See here, whenever we consider the work done to assemble the charges or to dissociate the charges from the assembly. So see here, the work done to assemble the charge, charges from one state to another state, another state. We have to keep this point in our mind, that is, work done is always equals to final potential energy minus initial potential energy. Okay, work done can be written as final potential energy minus initial potential energy. Okay, based on this formula. Okay, many times they have asked the question, in the NEET as well as previously AIMS papers. Okay, that is about the potential energy. And now, whenever we consider the potential energy of a dipole, simple system, that is a dipole, potential energy of a dipole. See here, minus q and plus q is a dipole, and the separation between the two charges or length of the dipole be, let it be 2a. Therefore, potential energy is equals to minus Pe into cos theta, or in vector form we can write minus P vector dot E vector, What is this P here? Where P is the dipole moment, as a dipole moment, and capital E is the external electric field, we can say external electric field, okay. And with the theta is the angle between electric field vector and the dipole moment vector, okay. So please make sure about this. And u is equals to, we can say, let us say special cases. Let us discuss about the special cases. We have to be very clear about this here. Potential energy, first one, when theta is equals to 0 degree. What is mean theta equal to 0 degree? Theta equal to 0 degree indicates that dipole moment vector is parallel to electric field vector. Dipole moment vector is parallel to the electric field vector. Then in this condition, u will become equals to minus P into E, and it is said to be minimum. Okay, and such condition, such position is there, no? The position of the dipole when the potential energy is minimum, or where the potential energy is a minimum, is said to be stable equilibrium position. We can say to be it is a stable equilibrium position. Okay. So please make sure you are understanding these points here. And later, second one, observe this. When theta is equals to 90 degree, theta equals to 90 degree implies dipole moment is perpendicular to electric field vector. In this situation, the potential energy of a dipole will be equal to zero, But many people think that whenever the potential energy is zero, that is taken as minimum, but that zero is not the minimum value. Minus PE will be the minimum value, that is when theta is equals to 0 degree. Okay, and second one, observe this. When so theta is equals to 180 degree, that is p vector is anti parallel to electric field vector, opposite electric field vector. That means, observe this, the dipole moment and the electric field vector both are acting in opposite direction. In such a situation, potential energy will become equals to plus P into E, and it is said to be maximum. Okay. So from and at this particular position here, this particular position of a dipole, that whenever the dipole moment is opposite electric field, we can say the dipole is said to be in unstable equilibrium position. So observe this. So theta is equals to 180 degree is said to be unstable. It is said to be unstable equilibrium position. Okay. So please make sure you are understanding these points clearly. Okay. So that is about the stable equilibrium position and unstable equilibrium position. I hope it is clearer to you. Whenever the dipole is having the minimum potential energy, then the dipole is said to be in a stable equilibrium position. When the dipole is having the maximum potential energy, then the particular position is said to be, what is that, unstable equilibrium position. Okay. And later, please make sure you are understanding these points clearly. And what is the work done? To rotate. A dipole. From theta 1 position to theta 2 position. From theta 1 to theta 2 is given by, so W is equals to, we can say PE into cos theta 1 minus cos theta 2. Work done is, as I said, work done is nothing but the change in potential energy. So please observe this. Work done is equals to PE into cos theta 1 minus cos theta 2. For example, suppose, see here, what is the amount of work done? To rotate a dipole. From stable equilibrium position, to unstable equilibrium position. What is the amount of work done here? Work done theta 1 stable in the sense theta 1 is equals to so is equal to 0 degree. Unstable is nothing but theta 2 is equals to 180 degree. Therefore, work done is equals to PE into cos theta 1 minus cos theta 2. So whenever we do simplification here, PE into 1 minus of minus 1, so W will become equals to 2 times P. This is the amount of work done to rotate a dipole from equilibrium position to an stable equilibrium position to unstable equilibrium position. Okay. I hope you understood how to apply this formula, Okay. So that is about the potential due to a point charge, potential due to system of charges, potential due to a dipole, and potential energy for the system of 2 charges, 3 charges, and also we can move on to the potential energy of a dipole. Okay. Now let us understand about what is the relation. What is the relation between electric field vector and the potential So see here, in one dimension we can write E is equals to minus dV divided by dx E is equals to dV by that is electric field is equal to negative potential gradient it is equals to negative negative potential gradient. Okay, and please observe this. What the negative sign indicate here? Negative sign indicates that electric field is always directed in the decreasing potential electric field is directed along the decreasing or it is directed from high potential region to low potential region. Okay, so let us understand about what can I say about in three dimension we can say that electric field vector is equals to minus dou v divided by dou r. What is r vector? R vector can be as xi cap plus yj cap plus zk cap. So dou by dou r indicates partial differentiation. So how to write this? I will explain. So please observe this. Whenever the potential is having the our potential is what is that potential is expanded in a space. Whenever there is a potential in a region or in a space, then we can say that E vector is equals to minus dou v by dou x into I cap minus dou v by dou y into j cap minus dou v by dou z into k cap. Or we can also write E vector is equals to Ex into I cap plus Ey into j cap plus Ez into k cap. Is it clear? So what is the Ex, Ey, Ez? That is nothing but the electric field intensity on x, y and z directions. So what is the magnitude? What is the magnitude of this electric field intensity? It is equals to square root of Ex square plus Ey square plus Ez square. This is the magnitude of electric field intensity. Okay, partial differentiation. What is meaning of partial differentiation? See here, whenever the v contains x, y and z terms, then we can say that so dou v by dou x, while we are differentiating with respect to x, we have to keep the y and z as a constant terms. And whenever we are differentiating v with respect to y, then x and z terms are taken as a constant terms. And whenever we are differentiating with respect to z, then we have to keep x and y terms as constant. Okay, I hope it is clear to you. This is the magnitude of electric field. Is equal root of ex square plus ey square plus ez square. Okay, and later we have to understand what is the equipotential surface. Here, what is the equipotential surface? So how can we define this equipotential surface? See here, surface on which okay, potential at every point, every point is same. It is said to be equipotential surface. Okay, and later no two equipotential surfaces intersect each other. No two surfaces will intersect each other. Okay, and later we have to analyze. See, observe this. The work done to move a charge. The work done to move a charge from one point to another point. On the equipotential surface. on equipotential surface is equal to 0, because each and every point will have the same potential, because of that reason work done will become equal to 0. Okay, and please observe this. Electric field lines, are always, perpendicular, electric field lines are always perpendicular to the equipotential surface. Okay, for example, so please observe this. For a uniform electric field, for example, observe this diagram or look at the diagram carefully. For uniform electric field, field, the equipotential surface will be a planar surfaces, So please observe these things here. This is the equipotential surface. Okay. So like that we have to think and we have to analyze the next point here. More, or we can say instead of this, we can say closer, the equipotential surfaces, closer the equipotential surface indicates stronger will be the field, stronger will be the field. Okay, and further the equipotential surface, further the equipotential surface, we can say weaker the field. So these are all the important points what we have to keep in our mind related to equipotential surface. Majorly these 2 points are very important here. And sorry, majorly we have to keep these points, this one and work done, and these 3 points are very important. So based on which we can expect the questions frequently or regularly, we can expect the questions. That is about the equipotential surfaces and important properties of equipotential surfaces. And later let's move on to the next point, that is polar and non-polar molecules here. What are these polar molecules? So see here, the molecules in which the molecules in which net dipole moment is not equal to 0. Suppose, or we can say that if the center of positive charges, and the center of negative charges, are separated by a finite distance, then they are said to be polar molecules. Okay, so please look at the board here. Whenever we consider a polar substance or polar dielectric, we can say that the center of negative charge and the center of positive charge is directed as shown in the figure. Okay, I hope it is clear to you. So therefore, each and every molecule will have a definite dipole moment. Okay, and please observe this. In the absence of external field, net dipole moment is equal to 0. In the absence of external electric field. Okay, what are the examples? For this we can say HCl or NaCl, or we can also say, okay, instead of this we can go with the H2O, etc. are examples of what is that? Polar molecules, okay. And later we have to understand about what is non-polar molecules. What are non-polar molecules? Okay, so please make sure about these things here. What are the non-polar molecules? Here the molecules in which the net dipole moment is equal to zero. Suppose, see here, how can you define this? If the center of positive charges if the center of positive and negative charges, if the center of positive and negative charges, if the center of positive and negative charges coincide, okay, then they are said to be, is it a non-polar molecule? Then they are said to be non-polar molecules. Non-polar molecule. So observe the diagram carefully. Whenever we consider the center of positive charge and negative charge here, so please look at the board carefully. I am writing the positive charge and negative charge as a circles, Is it clear? The center of positive and negative charges coincide, then they are said to be non-polar molecules. Okay, what are the examples? Whenever we go with the example, we can go with oxygen, nitrogen, etc. These are all examples of non-polar molecules. So see here, in the absence of external electric field, external electric field, we can say net dipole moment will be equal to zero. Either it may be polar molecules or non-polar molecules. In the absence of external electric field, both the molecules or both the dielectrics is said to have zero net dipole moment. Okay, so let us see here, what is the effect of okay, external electric field, on the dielectrics, So observe this. In case of non-polar molecules and non-polar dielectrics, each and every molecule can be considered as a dipole. And those dipoles will be aligned randomly, giving rise to net dipole moment is equal to zero. Is it clear? In the absence of external electric field. But whenever we place a non-polar dielectrics in the presence of external electric field, what happens? So please observe this. Let us say this is the external electric field. What this external electric field will do? This electric field will align those molecules, in such a way that it will possess the net dipole moment. This is in case of non-polar. In case of polar molecules also the same thing will happen here. In case of non-polar molecules, this electric field exert a force on the each and every molecule, and it will separate the center of positive charge and center of negative charge, Let us say E naught is the external electric field, So whenever we observe this, the ends of the dielectric, there will be positive charge at one end, negative charge at another end. Therefore, inside the dielectric, there will be induced electric field. Inside the dielectric, there will be induced electric field. So observe this. What is E naught? E naught is the external electric field. external electric field. External electric field. EI is the induced field, induced electric field. Therefore, the resultant or the net field is equals to E naught minus EI. Okay, that is a point we have to keep in our mind here. And later we have to understand if K is the dielectric constant. If K is the dielectric constant, then we can say that the resultant field is always equals to E naught divided by K. The resultant field is always be equals to external field divided by the electric field, that is the dielectric constant, constant. So like this. So in the presence of dielectric, external field decreases by K times. External field decreases by K times. That is the point we have to keep in our mind. Okay. And later we have to understand what is the electric polarization. What is electric polarization? Okay. So please observe this. What is electric polarization here? Electric polarization is nothing but the net dipole moment. Net dipole moment per unit volume. Net dipole moment per unit volume. Okay. So see here, electric polarization is denoted by capital letter P, and it is equals to net dipole moment per unit volume. So based on this, I think the previous year's NEET paper, they have asked a question. Okay. I hope you understood this question here. Net dipole moment is always be equals to, electric polarization is equals to the net dipole moment per unit volume of a substance. And later see here, electric polarization is directly proportional to the external field applied, electric field, external field applied. So removing the proportionality, I can write chi E. What is chi E into E naught here, where chi E is called as electric susceptibility, where chi E is called as electric susceptibility. Okay. So like this, we have to think and we have to analyze each and every formula and each and every concept, so that we can answer any question from this chapter, electrostatic, potential and capacitance. Okay, I hope it is clear to you. That is about the dielectrics, polar dielectrics, non-polar dielectrics, and what happens to net dipole moment in the absence of electric field and in the presence of electric field. What is electric polarization? And what is the induced field? And what happens to resultant field? In the presence of external, what is the dielectric? In the presence of dielectric. So what happens to the external field? Okay. So later we have to understand about what is a capacitor. So what is a capacitor here? We can say a device used to store energy, or used to store a charge, or energy in the presence of electric field. In the presence of electric field is called as a capacitor. Okay. So please observe this. Q is nothing but C into V. C is nothing but Q divided by V. What is the Q? Q is the charge given to a capacitor. Okay. And what is capital V here? Capital V is the potential, or rise in its potential. Rise in its potential. Is it clear? So please make sure you are understanding each and every point. And see here, for a given conductor, okay, capacitance remains constant. Capacitor remains constant. So see here, we can say for a given conductor, capacitance remains constant, remains a constant. Many people think that capacitance is directly proportional to charge and inversely proportional to potential of a conductor, but it is not correct because as the charge given to a conductor increases, the potential of a conductor also increases. Okay, that means as the numerator increases, denominator also increases, therefore capacitance will remain constant for a given conductor. Okay, and please make sure about this one here. And for a spherical conductor, let us say there is a conductor having the radius capital R, and capital Q is a charge given to it. Capital Q is a charge given to it. So therefore, the capacitance will be equals to 4 pi epsilon naught into capital R into capital R. That means for a spherical conductor, capacitance is directly proportional to the radius of a conductor. Okay, so like that we have to think and we have to analyze this point here. What is the SI unit? SI unit is a farad. SI unit is a farad. So please make sure about these things here. What are the other units? We use to for the measurement of capacitance. For the measurement of capacitance are microfarad. 1 microfarad is 1 into 10 to the power of minus 6 farad, and 1 picofarad is 1 into 10 to the power of minus 12 farads. These are the smaller units we can say. And observe this. So that is about the capacitor. That is about the capacitor. Now let us understand about what are the types of capacitor. So please make sure you are understanding each and every point here. Types of capacitors. Okay. Among them, the first one is parallel plate capacitor. First one is parallel plate capacitor. So please make sure you are understanding these points clearly. So let us consider the two plates. Usually capacitor consists of two arbitrarily shaped conductors. And those conductors are named as plates. So one plate is given a positive charge, let us say capital Q, and another plate is given a negative charge minus Q. Is it clear? So what is the D? D is the distance between the two plates, and capital A. Observe this. What is the Q? Q is the charge. On each plate. Charge on each plate of a capacitor. And D is the distance between the plates. And capital A is the area. Of each plate. Then we can say that capacitance. Capacitance of a capacitor C is equals to epsilon naught into A divided by D. This is in case of air, or in case of in air medium, in air or vacuum. We can say that is about the capacitance. Let us denote this C naught. C naught is nothing but capacitance of a parallel plate capacitor in the presence of air medium or in the presence of a vacuum between the two plates of a capacitor. Okay. Now later we have to understand, suppose if any dielectric is placed here, if a dielectric is filled, between the plates of a capacitor, between the plates of a capacitor. If a dielectric is filled between the plates of a capacitor, please observe this diagram carefully. This is a capacitor, and between the two plates, a dielectric is completely filled. Having the dielectric constant K. Then what is the new capacitance here? New capacitance is nothing but K into epsilon naught A divided by D. K into epsilon naught A divided by D. That means in the presence of a dielectric, capacitance will be increased by K times. Okay, I hope you understood this point clearly. And later observe this. If two or more dielectrics, are introduced between the plates of a capacitor, then we can say, please look at the board here. Let us say these are the two plates of a capacitor, and in between these two plates, let us say a one dielectric having the constant K1 and thickness T1, and another dielectric having having a constant K2 and thickness T2, and third dielectric, let us say having some constant K3 and thickness T3 has been introduced between the two plates. Then what can you say about the C effective here? What is the C effective? C effective will become equals to epsilon naught into A divided by D minus T1 by K1 minus T2 by K2. Okay, so please, so on we can say D minus T1 by K1 minus T2 by K2 plus so on. That is effective capacitance. Okay, sorry, I made a mistake here. Please, I will rectify this. This is not the exact formula here. T minus T1, okay, minus T2. Okay, I will write minus T minus outside. So on plus Tn. Okay, plus T1 by K1 plus T2 by K2 plus so on plus Tn by Kn. This is the effective capacitance of a capacitor when n number of dielectrics has been introduced between the two plates of a capacitor. Okay, I hope it is clear to you. Any confusion, you please comment so that I will go through it once more. So let us see, that is the effective capacitance of a capacitor, when two or more dielectrics have been introduced. Okay, so let us understand about the next point. What can you say about the, for example, suppose if a metal is introduced between the two plates of a capacitor, the two plates of a capacitor, as shown. Please have a look here. Whenever we consider a metal, let us say these are two plates of a capacitor and these are two plates of a capacitor here. And for example, if a metallic wire or metallic string or a conducting wire is connected between the two plates as shown like this here, then its capacitance becomes infinity because the dielectric constant for a metal is equals to infinity. Okay, so like that we have to understand these points clearly. So later we have to think about the second type of capacitor, that is cylindrical capacitor So it is not there in our NCRT, but it is mentioned in our what is it, NCRT exemplar. So what is a cylindrical capacitor cylindrical plate capacitor, cylindrical plate capacitor. What is cylindrical plate capacitor? So please observe this. When the two conductors are having the cylindrical shape, as shown in the figure, as shown in the figure. Okay, so please look at the board carefully. And inner plate is grounded, inner plate is grounded, and initially the conductor is having the radius A and the outside cylindrical plate is B. Cylindrical plate is B. Then what is the capacitance? What is the capacitance? Capacitance will become equals to, capacitance will become equals to, we can say that 2 pi epsilon naught into L ma. So it is nothing but 2 pi epsilon naught into L divided by log to the base E B by A. B by A. What is L? L is the length of a conductor, length of the plates of a capacitor. A is the radius of the inner plate and B is the radius of the outer plate. Is the radius of the outer plate. Okay. What is this? A. A is the inner plate radius, my inner plate radius, inner plate radius. B is the we can say outer plate radius, outer plate radius. Okay, so the L is the length of the plate. L is the length of the plate. L is the length of the plate. Okay, I hope you understood this point clearly. So similarly, we can move on to the next type of and that is a spherical plate capacitor. Here, what is the spherical plate capacitor? What is spherical plate capacitor? So please make sure you are understanding these points clearly. What is the spherical plate capacitor? Let us say here, in this capacitor, each and every plate, each plate will be in the shape of a sphere, in the shape of a sphere. So let us consider the one spherical plate having the radius A, and this is another spherical plate having the radius B, and inner plate is grounded. Inner plate is grounded. Then what is the capacitance of this plate, Maher? What is the capacitance? Capacitance of this plate is equals to 4 pi epsilon naught into AB divided by B minus A. AB divided by B minus A. There is a capacitance. What is the A here? A is the radius of the inner spherical plate and B is the radius of the outer spherical plate. Outer spherical plate. These are the different types of capacitors. Okay, and later we can move on to the what is the series combination of the capacitor. What is the series combination of the capacitors, so please observe this. Generally, whenever we consider the capacitors connected in series, that is positive plate of one capacitor should be connected to, negative of one plate. Negative of one plate is connected to the positive of another plate. Then it is said to be series combination. Let V be the applied potential. V is the applied potential. So in series combination, charge on each plate remains constant. And net potential difference will be equals to V1, and this is V2, and this is V3. V is equals to V1 plus V2 plus V3, V1 plus V2 plus V3. So what is this C1, C2, C3 are the effective capacitance. Then we can say that how can you calculate V1? V1 can be written as a charge divided by C1, and V2 is equals to charge divided by C2, and V3 is equals to charge divided by C3. Okay, so like this we have to find out the individual potential difference. And what can I say about the effective? C equivalent. Okay, I will write directly 1 by CS. 1 by CS is equals to 1 by C1 plus 1 by C2 plus 1 by C3. This is the effective capacitance of three capacitors in series. Okay, so please make sure about these things here. And later we have to understand the things for two capacitors, for two capacitors in series, the two capacitors in a series, what is effective or CS will become equals to C1 C2 divided by C1 plus C2, C1 C2 divided by C1 plus C2, and the charge will remain same, no? So C1 V1 and this C2 V2. Therefore, we can write V2 can C1 into V1 divided by C1 plus C2. C1 is it clear? C2 we can write. Is it clear? These are individual things. If V is the applied potential, V is applied potential, then how to write this? V can be as V1 plus V2, V1 plus V2. So if you do substitution here, substitute the value of V2, substitute the value of V2 in this equation, and if you simplify for V1, then you will get, V1 is equals to C2 into V divided by C1 plus C2, C1 plus C2. If you want, you can check it here. So V1 plus V2 is nothing but, you can say like this, C2 into V divided by C1 plus C2. This is the potential across the first capacitor. And what is V2 value? V2 is equals to C1 into V divided by C1 plus C2. C1 into V divided by C1 plus C2. That is the thing we have to keep in our mind. I hope you are understanding each and every point. Okay. So like this, we have to think and observe this. We can say, okay, I hope you understood this one. The shortcut formula with which I can easily calculate the individual potential difference across each capacitor, okay. And please make sure about these things clearly. And for n identical capacitors, we can say CS will become equals to C divided by N, C divided by N. And series combination is used series combination is used to get the low capacitance value, to get the low capacitance value. Series combination is used whenever we require the low capacitance, okay. That is about the series combination of the capacitors. And how to calculate the potential difference across the individual capacitors. This is the one way of calculating the individual potential differences when we know the charge on each plate of a capacitor and the capacitance of each capacitor. Suppose if I know what is the applied potential, and this formula can be applied only for two capacitor. This formula can be applied only for two capacitor. Maximum to maximum, they will ask only two capacitor combination only at this level, that is NEET level. So no need to worry about this. So later we can move on to the parallel combination. Here parallel combination, okay. Parallel combination of capacitors, okay. So please make sure I am writing only important points. First one, in parallel combination, we can say potential difference will remain constant. Potential difference will remain constant. And what can I say about the total charge here? Total charge will become equals to Q1 plus Q2. Let us call this as equation 1. So observe this. These are the three capacitors. These are three capacitors which are connected, in parallel combination, okay. And this is the applied potential. If this applied potential, if V is the applied potential, So please make sure about this. Potential difference across each and every capacitor will remain same. So observe this. If Q is the total charge, Q1 is a charge on the first capacitor, and Q2 is a charge on the second capacitor. Q3 is a charge on a third capacitor. Okay. So total charge will become equals to Q1 plus Q2 plus Q3. Also we can write, let us say, Q1 plus Q2 plus Q3 for three capacitors. For three capacitors. So therefore, how to calculate this Q1 value here? Therefore, Q1 can be written as C1 into V, and Q2 can be as C2 into V, and Q3 is equals to C3 into V. This is the charge of individual capacitor, charge on individual capacitors. Now, what can I say about the equivalent capacitance here? Equivalent capacitance. So please observe this equivalent capacitance in parallel combination. We can write C1 plus C2 plus so on Cn for Cn. Okay, and for for two capacitors, we can write Cp is equals to just C1 plus C2, and for n identical capacitors we can say Cp is equals to n times C. So please observe this parallel combination is used to get high capacitance. Parallel combination is used to get the high capacitance. Okay, Cp is equals to C1 plus C2 for two capacitors. For n identical capacitors, Cp is equals to n times C. So please observe this. What is the relation? Cp is always equals to n square times Cs. N square times C. That means n identical capacitors first connected in parallel combination and then connected in series combination. Then we can say the relation between the effective capacitance in parallel and series is always equals to Cp is equals to n square times Cs, n square times Cs. Okay, I hope you understood these points clearly. Later we have to understand what is the energy stored. What is the energy stored in a capacitor? What is the energy stored in a capacitor? So please observe this. What is energy stored in a capacitor? So we can say U is equals to half CV square. Otherwise, we can say half Q into V. Otherwise, we can say Q square divided by 2C. Q square divided by 2C. Okay, that is about the potential energy. And here we have to observe clearly. So observe this. If whenever the potential difference is constant, so in which condition the potential difference will remain constant, especially in parallel combination. So when the potential difference is constant, we can say potential energy is directly proportional to capacitance, and potential energy is directly proportional to the charge on a capacitor. Okay, and similarly whenever the charge remains constant, second case, if the charge remains constant, then we can say that potential energy is inversely proportional to capacitance, and potential energy is directly proportional to the potential difference between the two plates. So like this, we have to analyze how the potential energy depends on charge and the potential difference between the two plates on each case. Okay, and later we have to understand what is the energy density. So please have a look here. What is energy density here? Energy density usually denoted by small letter u. Small letter u. It is equals to energy stored per unit volume. Energy stored per unit volume. It is equals to, we can show it is half epsilon naught into E naught square. Half epsilon naught into E naught square. That is the expression for potential energy density. Potential energy density. Okay. I hope you understood this clearly. Now let us see how to calculate the common potential. So please have a look here. Have a look here. Let us consider a capacitor. Let's consider a capacitor having the C1 capacitance and which is charged to a potential V1, and Q1 is the charge on the plates of a capacitor, charge on the plates of a capacitor. Now what can you say? Observe this. So it is charged by a battery, Then observe this. Now what we are saying here, disconnecting the battery has been removed, and this capacitor C1 is connected to another capacitor C2. Initially let us say this is a V2 potential. Let us say this is another capacitor having the capacitance C2, which is also charged to a potential V2. Will have the charge on the plates of the capacitor as Q2. Then whenever these two plates or whenever these two capacitors has been connected, then we can say the combination will be in parallel combination. Is it clear? So V1 is the potential of the first capacitor, V2 is the potential of the second capacitor. We can say that what can you say about the common potential? Okay, so please observe this. Common potential VC becomes equals to, you can say, C1 V1 plus C2 V2 divided by C1 plus C2. So what is the basic idea behind this? Is nothing but total charge, that is Q1 plus Q2 divided by C equivalent. This is the basic idea behind this formula. And later we can also say what is the loss of energy during this process. We can say delta U is equals to half into C1 C2 divided by C1 plus C2 into we can say that V1 minus V2 whole square. This is a loss of energy during this process. What is energy stored in the first capacitor? It is half C1 into V1 square, and is that energy stored in second capacitor is half C2 into V2 square. Is it clear? So whenever we do like this, there will be certain loss of energy, and it is equals to half C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. What is V1? V1 is the potential difference across the first capacitor, and V2 is the potential difference across the second capacitor. This is the shortcut formula we have to keep in our mind. Okay, and one more thing, this formula plus is obtained when the positive plate of one capacitor is connected to positive plate of another capacitor. Is it clear? I hope it is understanding. Suppose if the positive plate of one capacitor is connected to negative plate of another capacitor, then the common potential becomes C1 V1 minus C2 V2 divided by C1 plus C2. I hope you understood this. So please listen to the sentence properly. Okay, that is about the how can we calculate the common potential and loss of energy. And later, please observe this. So effect of dielectric. So let us understand effect of dielectric. Effect of dielectric. Effect of dielectric in the two cases. First case, that is the battery is not disconnected. My battery is connected. Let us say battery is connected to a capacitor and the battery is disconnected. Battery is disconnected to a capacitor. Okay, so please make sure you are understanding these points here. What is effect of dielectric? So please look at the board here. Let us consider a capacitor. Initially the battery is connected as shown. Now a dielectric is introduced between the two plates of a capacitor having some dielectric constant K. Then what can you say about the things or physical quantities? So whenever the battery is connected and the dielectric is introduced, first thing we have to understand potential difference across the plates of a capacitor will not change. Whenever the potential difference will not change, we can say electric field intensity between the plates will not change. And observe this, whenever the dielectric is introduced, the new capacitance will be increased by k times. Okay, and later we have to understand what is the charge stored on the capacitor will also be increased by k times. Now, what can you say about the energy stored on the capacitor U dash? Energy stored on the capacitor U dash. See here, whenever the potential difference is constant here, whenever the potential difference is constant, and then we can say energy stored is directly proportional to charge. Is it clear? Therefore, potential energy will also be increased by initial potential energy k times, increased by k times. These are the things what we have to keep in our mind whenever the battery connected to a capacitor is not disconnected and a dielectric is introduced. Okay, now let us move on to the second case here. When the battery connected to a capacitor is disconnected and a dielectric is introduced between the plates of a capacitor. So one thing, whenever the battery is disconnected and whenever dielectric is introduced, we have to think that the charge on the plates of a capacitor will not change. It remains constant. And we can say potential difference will be decreased by k times and dielectric field intensity is also decreased by k times. Okay, so these are the things we have to keep in our mind directly so that we can save our time. Okay, now what can you say about the capacitance here? Capacitance will be increased by k times. Capacitance will increased by k times. Therefore, what can you say about the potential energy here? Whenever the charge is constant, please observe this. Whenever the charge is constant, potential energy is directly proportional to the applied potential difference. Therefore, we can say initial potential energy divided by k times. Okay, so these are all the points what we have to learn and what we have to keep in our mind so that we can answer the questions. From the chapter electrostatic potential and capacitance. Okay, I hope it is clear to you. So please prepare well. Okay, we can answer any MCQs from this chapter in the NEET entrance examination. Okay, now let us move on to the what is that MCQs in multiple choice questions and also previous years what is that questions which are given from this particular chapter in the NEET entrance examination. Okay, let us see those questions, then you will get an idea what level of questions has been asked in the previous year's papers and what should be our preparation and how should I prepare. But I request everyone, before going to solve the MCQs, Please practice and understand these concepts as many times as possible, possible. Okay, I hope you can do this. I hope, okay, you can do this. Let us see. Let us see the first question. Let us see the first question. What they are saying to us. Please read this question carefully. What they have given to us. Please read this question. The value of electric potential at a distance of 9 centimeter from the point charge 4 into 10 power minus 7 coulomb E. See, this is the question which is asked in the recent 2024 paper. If you want, you can check it. If you want, you can check it. So see here, distance r is equals to 9 centimeter and the point charge, what is the charge given? 4 into 10 to the power of minus 7 coulomb. Therefore, what is the potential? Potential is equals to 1 by 4 pi epsilon naught into q by r. See, observe this is a direct formula based question they have asked in the previous year, that is the 2024 paper my year. So charge is 4 into 10 to the power of minus 7 divided by distance is 9 into 10 power minus 2. Whenever we do simplification, then we get 4 into 10 to the power of minus 2. It is plus 2 plus 2. It is equals to 4 into 10 to the power of 4 volts. Hence, we can select option D as the right answer. Option D is the right answer. Okay. I hope you understood this question clearly. So move on to the next one. What they are saying to us: a 12 picofarad capacitor is connected to a 50-volt battery. The electrostatic energy stored in the capacitor in nanojoules. They are asking in nanojoules. So observe this. What is the capacitor? They have given 12 pico means 10 to the power of 12 farad and potential applied is 50 volt. Therefore, potential energy is equals to half CV square. So half into C is 12 into 10 to the power of minus 12 into V square is 50 into 50. So 2126 it get cancelled here. So observe this 6 into 5 300, 3 into 50 1500. Is it clear? Into 10 to the power of into 10 to the power of. You please calculate this value once. How much you are getting this value? Please check it here. 1500, that is 15,000 into 10 to the power of minus 12 you will get. So 15 into 10 to the power of minus 9 joules, which is nothing but 15 nanojoules. 15 nanojoules. Hence you can select option A as a right answer. Option A is right answer. Is it clear? I hope you are understanding these points clearly. Let us see the next question. What they are saying to us. Please read this problem here. The capacitance of a capacitor with a charge Q and a potential difference V depends on. So see here, whenever we observe capacitance of a capacitor, it is equals to epsilon naught A by D. Epsilon naught A by D. So capacitance of a capacitor depends on area of cross section of each plate and the distance between the two plates and the dielectric medium placed between the plates of a capacitor. So we can say both Q and V know geometry of the capacitor. Yes, we can select option B as the right answer. Option B is the right answer. Similarly, move on to the next one. What they're saying to us: a thin spherical shell is charged by some source. The potential difference between the 2 points C and the P is shown in the figure is. What is the potential difference across the point C and across the point P? They are asking here. So please observe this. We know that potential inside is always equals to potential on the surface. It is equals to V. Therefore, what is the potential difference between the point C and the point P? It is equals to V minus V. It should be equal to 0. Hence, we can select option D as the right answer. Option D is the right answer. I hope you are understanding each and every point here. So move on to the next question. What they are saying to us. So please read this question here. In the following circuit, the equivalent capacitance between the terminals A and the terminal B is. They are asking us to calculate what is the equivalent capacitance. So whenever you observe this circuit properly, then it resembles. So please think about this. The circuit is similar to Wheatstone bridge. So please look at the board here. Wheatstone bridge. So whenever we move on to this, let us say this is the P, Q, and this R, and this is a S. Is it clear? It resembles Wheatstone network that way, in which we can say P by Q is equals to R by S, which is equals to 1, Therefore, we can eliminate this 2 microfarad capacitor, Therefore, what is this effective capacitance of this upper branch here and effective capacitance of this lower branch? So let us call this as CS1, and this is CS2, CS2. So calculate what is CS1 here. CS1 will become equals to, directly I am substituting 2 into 2 divided by 2 plus 2. You can say 4 divided by 4, which is nothing but 1 microfarad. Similarly, CS2 is also equals to 2 into 2 divided by 2 plus 2, which is nothing but 4 by 4, which is nothing but 1 microfarad. Therefore, effective capacitance are in a parallel combination of CS1 and CS2, which is nothing but 1 plus 1, which is equals to 2 microfarad. Hence, we can select option A as a right answer. Option A is the right answer. Is it clear? I hope you're understanding these points clearly. Whenever we come across such circuits, first we have to check the balancing condition of Wheatstone network. So move on to the next one, what they are saying to us. So observe this. If the plates of a parallel plate capacitor connected to a battery are moved close to each other, implies the distance is less than the initial distance. A charge stored in it increases, the energy stored in it decreases, its capacitance increases, and D, the ratio of a charge to its potential remains the same. Charge to its potential. The ratio of charge to its potential remains same is nothing but the capacitance only here. The product of charge and voltage increases. Product of charge and potential increases. Choose the most appropriate answers. Okay. So please observe this, what they are saying to us. So whenever we consider the capacitance of a capacitor, C is equals to epsilon naught A divided by D. So when D is decreased, then we can say that capacitance will be increased. So we can say whenever capacitance is increased, charge stored will also be increased. Is it clear? Charge will also increase. Therefore, we can go with energy stored. What can you say about the energy? What can you say about the energy store? Charge stored. Charge stored in it is increased. Increased. So we can select option A. Sorry, option A. We can go with the sentence. Statement A is correct. Statement A is correct. Is it clear? And whenever we go with the energy stored, whenever the charge is increased and capacitance is increased, then we can say that energy will remain constant. Because energy is equals to half C dash into V square. So energy should increase actually. When capacitance is increasing, therefore energy should be increased. Capacitance increases. Yes, it is also right statement. The ratio of charge to its potential remains constant. What is the charge to potential here? Charge by V will not remain constant. Okay. The product of charge and potential increases. So observe this. The product of charge Q dash. Since Q dash is increasing, so Q dash into V also increases. Hence we can select A, C and E, A, C and E, which indicate option B as the right answer. Okay. I hope you are understanding these points. So move on to the next question, what they are saying to us. So observe this. A parallel plate capacitor is charged by connecting it to a battery through a resistor. If I is the current, in the circuit, then the gap between the plates is, then in the gap between the plates, there is no current. The displacement through current magnitude equal to
magnitude equal to what is the value of this I? Magnitude equal to I flows in the same direction as I. Displacement current of magnitude equal to I flows in direction opposite. No. So observe this. Whenever we consider the two plates of a capacitor, whenever two plates of a capacitor, and whenever it is whenever it is charged with the help of a battery, there should be growth of charge. If I is a conduction current, then when the current is flowing, the charge on each plate of a capacitor goes on increasing. Therefore, the electric field between the plates will be increasing. Therefore, there will be a displacement current equal to the magnitude of the conduction current. In electromagnetic waves, so you learn about these things in depth. So in the same direction of the current, conduction current. So we can go with there will be a displacement current. What is meaning of displacement current? Displacement current is nothing but the current between the plates of a capacitor because of varying electric field. Okay. Hence we can select option B as the right answer. Option B as the right answer. I hope it is clear to you. Similarly, let us move on to the next question. Let us move on to the next one. What they are saying to us. Please read this question. An electric dipole is placed at an angle of 30 degree with an electric field of intensity 2 into what is the theta? They have given 30 degree, and what is the electric field intensity? They have given 2 into 10 to the power of 5 Newton per coulomb. It experiences a torque equal to 4 Newton meter. Calculate the magnitude of charge on the dipole. What is the length of the dipole? They have given 2 centimeter. I hope you have learned this in the last class only, my last video, that is in the last chapter, electric charges and fields. So please take this problem as a homework. Then you should get the answer. I should get the answer as 2 millicoulomb. Okay, I hope you can do this. You can do this. So similarly, move on to the next one. What they are saying to us: the equivalent capacitance of the system shown in the following circuit is. So please observe this. This 3 microfarad is in series with these two 3 microfarad capacitors in parallel. So first of all, you calculate these two here. Cp is equals to 3 plus 3, which is equals to 6 microfarad, because in Cp parallel combination effective capacitance is C1 plus C2. Therefore, please observe this. This is the 3 microfarad capacitor, and which is in series with the Cp, which is equals to 6 microfarad capacitor. This is a point B. This is a point B. Therefore, let us call this as C1. Therefore, what is the C across AB? Series, no series combination. We can C1 into Cp divided by C1 plus Cp. What is C1 value? 3 into 6 divided by 3 plus 6. 18 divided by 9, which is nothing but 2 microfarad. Hence we can select option D as a right answer. Option D is a right answer. I hope you are understanding these points clearly. Now similarly, move on to the next question. What they are saying to us. Please read this question here. Please read this question. The electric dipole is placed as shown in the figure. Electric potential in 10 square, man. It cannot be 10, not 2. It should be 10 square. It should be 10 square volt. It should be in a 10 square volt here. At point P, due to the dipole, is epsilon naught. What is epsilon naught? Epsilon naught is the permittivity of the free space. So what is the potential? At the point P? P. So please observe this. Dipole is nothing but the system of two charges. Let us say this is the first charge and this is the second charge. The first charge is at a distance of 8 centimeter. Therefore, the net potential at the point P is always equals to V1 plus V2. So what is the V1 value? 1 by 4 pi epsilon naught into, we can say Q1 divided by R1 plus Q2 divided by R2. So just substitute the value of this here. 9 into 10 to the power of 9 into what is Q1? Q1 is equals to what is the charge they have given to you? They're asking us to calculate what is the charge. Okay, let it be Q only. Q. Better. You replace this 1 by 4 pi epsilon naught as K into Q divided by R1. R1 is 8 centimeter. So 10 to the power of minus 2, we'll take it out. Okay, minus Q2. Q2 is nothing but minus, okay, let us say it is minus and this is a plus Q divided by 5. Divided by 5. So please do simplification. You can say K into Q divided by 10 power minus 2 into minus 1 by 8 plus 1 by 5. So whenever we do simplification, here potential the point B becomes equals to K into Q into 10 power 2 into, we can say take LCM of this here. So how much you are getting? How much you are getting? 5 minus 5 plus 8. Minus 5 plus 8 is nothing but 3 divided by 32 something I am getting here. 32 divide something I am getting. But I am not having the exact value of this, no. Exact value. Please check it once. Please check it once. How much you are getting here from, sorry. I'm doing mistake here. So it is not 5. It is not a 5 because from the second charge, the distance is at a distance of only 2 centimeter. 2 centimeter. Therefore, it should be equals to 1 by 2. 1 by 2. So please do this properly here. Whenever we go with the LCM, so it should be equal to, LCM is 16, let us say 16. Okay, minus 2 plus 8, So V at the point P is equals to KQ into 10 to the power of 2 into plus 6 divided by 16. So we can say 2, 8, 2, 3. Therefore, it becomes equals to 3 by 8 times K into Q into 10 power 2 volt. I am getting 3 by 8. 3 by 8 in the sense we can go with the option D as a right answer. Option D is the right answer. Okay. I hope it is clear to you. So please make sure you are understanding these points clearly. Now similarly, move on to the next question. According to Gauss law of electrostatics, electric flux through a closed surface depends on, okay, sorry, it is a repeated, not repeated from the previous chapter. So you please answer to this question. Question. You will get it, as option B. So you know that according to Gauss law, the total flux is always equals to 1 by epsilon naught times the charge enclosed. You please make it fast. So move on to the next one. The charge Q microcoulomb is placed at the center of a cube. So please do it properly and take this problem as a homework. And you should know that total flux is equals to Q divided by epsilon naught. So whenever we do this, then you should get the answer as Q divided by 6 epsilon naught into 10 to the power of minus 6. They're asking only out from any one of the phases. Please observe and do it in a proper way. Okay. I hope you can do it. Do it. So see the next one, what they're saying to us. The distance between the two plates of a parallel plate capacitor is doubled. Okay. And the area of each plate is halved. If C is its initial capacitance, its final capacitance is equal to. So in the first case, let us say, capacitance is equals to epsilon naught into A divided by D. In the second case, we can say C dash is equals to epsilon naught A by 2 divided by doubled in the sense 2D. So just do simplification, epsilon naught into A divided by 4D, you will get it. So you can say it is equals to C by 4. Hence option A is the right answer. Option A is the right answer. Okay. I hope you're understanding these questions clearly. Is it clear? So like that we had, these are all the questions which are asked in the paper 2022 2022 NEET paper, 2022 NEET paper. Okay. So observe this. What is the level of the questions? You will get a clear picture. You will get a clear picture, so that we have to prepare nicely. So move on to the next one. What they are saying to us: the effective capacitance of the two capacitors are 3 microfarad and 16 microfarad when they are connected in series and parallel respectively. The capacitance of the two capacitors are, what is the capacitance of two capacitors? So when they are connected in series, it is equals to 3 microfarad, and when they are connected in parallel, it is equals to 16 microfarad. What is series combination? We can say C1 C2 divided by C1 plus C2, which is equals to 3 microfarad, and here it is C1 plus C2 is equals to 16 microfarad. Instead of solving this problem through a regular mathematical stepwise procedure, better you go with option verification technique. So parallel C plus 2, we can say parallel combination is equals to 16 microfarad, 16 microfarad, in the sense there is only two options, that is B and C. You please check only this option B and option C here. So let us check option B. C1 is equals to 10 microfarad and C2 is equals to 6 microfarad. So please check it here. CS 10 into 6 divided by 10 plus 6, which is equals 60 divided by 16. You will not get it. The thing here. Is it clear? CS. What is the value of the 16? 4 something you are getting. So you're not getting the exact answer. Okay, sorry. Let us check option this one also. So option C, let us check. 8 into 8, 8 into 8 divided by 8 plus 8. So see here 64 divided by 16 is also 16 4 something I am getting here. So better go with option D. Option D, that is a 12 into 4 divided by 12 plus 4, which is nothing but 48 divided by 16, which is equals to 3 microfarad. Hence we can select directly option D as a right answer, so that we can save our time. If you apply the formula and if you go accordingly mathematical procedure, then it is a lengthy process. Better such type of problems, or this type of problems, can be solved by option verification technique. Okay, I hope you understood these things here. So similarly, move on to the next question. What they are saying to us. Please read this. 6 charges plus Q minus Q plus Q minus Q plus Q and minus Q are fixed at the corners of a hexagon of side D, as shown in the figure. The work done in bringing a charge Q naught to the center of the hexagon from infinity is. So what is the work done from infinity is here. Work done is always equals to the charge moved into final potential V at the center O minus V at the initial infinity. So let us call this as equation 1. So whenever we observe the potential at the center O, we can say K divided by, what is the distance of this center from each corner, they have mentioned it is equals to D. So K divided by D into, what is the value of charges here? Plus Q minus Q plus Q minus Q plus Q minus Q. So all the net charge is becoming equal to 0. Therefore, we can say V at the center is equal to 0. And we know that V at the infinity is also equal to 0. Therefore equation 1 implies work done must be equal to 0. Hence we can select option B as a right answer and option B as a right answer. Okay, I hope you understood this question clearly. So move on to the next one. the angle between electric field lines and electric field lines of force and equipotential surface. And I said to you that electric field lines are perpendicular to equipotential surfaces always equipotential surface. Therefore, the angle between the field lines and the potential surface always be equals to 90 degree. Okay, I hope you are understanding these questions clearly. Now similarly, move on to the next question. What they are saying to us. Please read this question, please read this question. A capacitor of capacitance C equals to 900 microfarad is charged fully by 100 volt battery B as shown in figure A. Then it is disconnected from the battery and connected to another uncharged capacitor. So observe this. V1 is equals to 100 volt and V2 uncharged. When they have mentioned uncharged, V2 will become equal to 0. Now what is C1 value here? C1 equal to C2, they have mentioned it as 900 picofarad. The electrostatic energy stored in the system B is. What is electrostatic energy stored in the system B is? How can we do this question? See, they are not asking what is the loss of energy in doing this process. They're asking only what is energy stored in the figure B, Therefore, see here, whenever we observe the figure B, we can say that what is the C equivalent value here, C1 plus C2, which is nothing but 1800 picofarad. Now, what can you say about the common potential? Common potential is C1 V1 plus C2 V2 divided by C1 plus C2. So just calculate this value here. C1 is 900 into 10 to the power of minus 12 into V1 is 100 plus C2 V2 is 0 because V2 is equal to 0 divided by C1 plus C2 is 1800 into 10 to the power of minus 12. So whenever we go with the common potential becomes equal to, there is we can observe this 10 power minus 12 will get cancelled, two zeros will also get cancelled. We can say 900 divided by 18. So please do simplification, then you will get the answer as a common potential will be 50 volt. Then what is the potential energy? Therefore potential energy in the second case becomes equals to half into C equivalent into V common square. So half into C equivalent. What is C equivalent value here? 1800 picofarad into V common square. V common square is 50 into 50. 50 into 50. So please do simplification. 900s here. So we can say 5 into 5, 25. 25 into 9 means 225 into 10 to the power of minus 8 joules we are getting here. 225 into 10 to the power of minus 8. It can be written as 2.25 into 10 to the power of minus 6 joules. Hence, we can select option C as the right answer. Okay. I hope it is clear to you. Is it clear, students? Now, similarly, move on to the next question. What they have given to us. Please read this problem here. The equivalent capacitance of the combination shown in the figure is. What is the equivalent capacitance of the combination shown in the figure? So please think about this. What they are saying to us. So whenever we move on to the figure carefully, whenever you observe the circuit diagram carefully, let us imagine the one end of this combination is connected to the battery, positive terminal of the battery, and the other end is connected to a negative terminal of a battery. Let us imagine that. So let us see here. A charge is flowing from the battery. So please think about this. We can say that the charge which is entering to this junction will get splitted into two parts. But whenever we observe this C capacitor, third capacitor, and it is in, there is one, what is that? Short circuit. This capacitor, this third capacitor is short circuited, is a short circuited between these 2 points. Therefore, the charge will not flow through this capacitor. The charge will come like this, and it will come out of this circuit. Is it clear? Since this capacitor C is short circuited, no charge will flow through this capacitor. Therefore, this capacitor will be ineffective. Therefore, we can say that C equivalent becomes equals to C plus C, which is nothing but 2C, nothing but 2C. Hence, we can select option B as the right answer, option B as the right answer. Okay, I hope it is clear to you. Now, similarly, move on to the next one. What they are saying to us, observe this. Two charged spherical conductors of radius R1 and R2 are connected by a wire. The ratio of surface charge densities of the spheres is. They're asking what is the ratio of surface charge densities. Okay. So please observe this. What is surface charge in the first sphere? We can say Q1 divided by what is the area 4 pi R1 square and surface charge density sigma 2 of the second sphere is Q2 divided by 4 pi R2 square. Now take the ratio here, sigma 1 by sigma 2 is equals to, we can say Q1 by R1 square into R2 square divided by Q2. Is it clear? Let us call this as equation 1. Equation 1. Now observe this. When they are connected by a sphere, when they are connected by a conducting wire, they will share their charges until their potential difference or potential remains same. Then from this we can say Q1 by R1 will become equals to Q2 by R2. Therefore, you can say Q1 by Q2 becomes equals to R1 by R2. So just substitute the value of this here. Sigma 1 by sigma 2 becomes equals to Q1 by Q2 is nothing but R1 by R2 into R2 square divided by R1 square. So whenever we do simplification here, 1 R1, 1 R2 will get cancelled. It becomes equals to R2 divided by R1, R2 divided by R1. Hence we can select option B as the right answer. Option B is the right answer. Okay. I hope you're understanding each and every step here. So move on to the next question, what they have given to us. Please do this. They're asking what is the energy stored in the capacitor? What is the energy stored in the capacitor here? So how can we do simplification? Please observe this carefully. In a parallel plate capacitor, okay, what is the distance of separation between them? It is D. And what is the capital A? Capital A is the area of each plate, But whenever you observe the options, options are given in terms of epsilon naught into E square, Therefore, please observe this. We know that energy density small letter u is equals to energy per unit volume, and it is equals to half epsilon naught into E square. Is it clear? Therefore, they are asking only U. They are asking only U, energy. Therefore, U becomes equals to half into epsilon naught into E square into volume, But this volume here, we can say half epsilon naught into E square into volume. Volume can be written as area of each plate into the distance between the two plates. So actually, this is not capital D. This is not capital D. It should be small letter D. D. This is a typing error. Okay. Hence, we can go with the option C as the right answer. Option C as the right answer. I hope it is clear to you. So please move on to the next question. What they are saying to us. Please think about this. 27 drops of same size are charged at 220 volt each. They combine to form, a bigger drop, calculate the potential of the bigger drop. What is the potential of the bigger drop? Okay, so how many drops we are having here? How many drops we are having? So please observe this. What is the potential of each drop? Potential of each drop is 220 volt, and number of drops is equals to 27. And observe this, potential of the bigger drop, they are asking us to calculate. So how can we do this? So see here, whenever the n number of drops, spherical drops, are combined to form together, the total charge becomes equals to n times the charge of smaller drop, And what is the radius of the bigger drop here? Radius of the bigger drop becomes equals to n to the power of 1 by 3 times the radius of the smaller drop. Okay. Therefore, please observe this. What is the potential of the smaller drop? It is equals to k into small q divided by small r. Therefore, what is the potential of the bigger drop here? We can say k into capital Q divided by capital R. So k into, what is the capital Q? We can write n into small q divided by capital R is nothing but n to the power of 1 by 3 into small r. So you have to remember these shortcuts, then only you will get a clear picture. So it becomes equals, whenever we do simplification, n to the power of 1 minus 1 by 3, it becomes equals to 1 minus 1 by 3, which is nothing but n to the power of 2 by 3 into potential of the smaller sphere. Okay, so just to do simplification here, potential of the bigger drop becomes equals, what is n value? N value is 27 whole to the power of 2 by 3 into what is the potential of smaller? It is 220. It is 220. Please do simplification. Then you'll get so 3 cube. 27 can be 3 cube. Cube and cube 3 will get cancel. 3 square. 3 square into 220. 3 square into 220. It is 9 into 220. So whenever we do multiply this, we can say 1980 volt. We will get it 1980 volt. Hence option D as the right answer. Option D is the right answer. How we get this relation here? Please observe this. Volume of the bigger sphere is always equals to n times the volume of a smaller sphere. So whenever we do this, then you will get the relation between the radius of the bigger drop and the radius of the smaller drop. Okay, I hope you can do such type of things, and you can remember this as a shortcut formula. Potential of the bigger drop is equals to n to the power of 2 by 3 times the potential of smaller drop. Okay, I hope you can do this. Now similarly, move on to the next question, what they are saying to us. Read this question carefully. A spherical conductor of radius 10 centimeter has a charge 3.2 into 10 power minus 7 coulomb distributed uniformly. What is the magnitude of electric field at a point 15 centimeter from the center of the sphere? I think it is repeated question, sorry. So from the previous chapter, okay. So please do this question by yourself. Then you should get the answer as 1.28 into 10 to the power of 5 Newton per coulomb. Please comment your answer. Do this problem. You will get a practice. Okay. There is no loss. There is nothing to loss. So move on to the next question. Please read this. I hope you can do it, ma. A short electric dipole has a dipole moment. Dipole moment is 16 into 10 to the power of minus 9 coulomb meter. The electric potential due to dipole at a point at a distance of 0.6 meter from the center of the dipole situated on a line making an angle of 60 degree. With the dipole axis is. So I think you can do this. Potential due to dipole is equals to 1 by 4 pi epsilon naught into P cos theta divided by R square. Just apply this formula and do by yourself. This is a direct formula based question. Hence, whenever we do simplification, we should get the answer as approximately 200 volt, 200 volt. And these are all the questions which are asked in the previous year's papers. Okay, I think you are understanding, okay, what type of questions has been asked in the previous year's papers. And if you prepare these models, it is more sufficient. Happily, you can attend the questions from this chapter, electrostatic, potential and capacitance. Okay. So move on to the next one, what they are saying to us. Please read this question here. The capacitance of a parallel plate capacitor with air as medium is a 6 microfarad. That is, they have given C0 is equals to 6 microfarad. With introduction of dielectric medium, the capacitance becomes 30 microfarad. Then what is the permittivity of the medium is given? Capacitance become 30 microfarad. Then what they are asking us to calculate here? They're asking us to calculate. What is the permittivity of the medium. They're asking us to calculate what is the permittivity of a medium, that is epsilon. They're asking us to calculate. Okay, how can we do this? Please have an idea. Epsilon is equals to epsilon naught into epsilon r. Usually epsilon r can be as a dielectric constant. Okay, so this is the formula we require. Let us call the equation 1. So see here, we know that capacitance in any medium is equals to K times the capacitance in the air medium. So observe this. What is the Cm value? It is the 30. K into C naught is the 6. So whenever we do this, K becomes equals to 30 divided by 6, which is equals to 5. We'll get the value of K equal to 5. Therefore, calculate epsilon is equals to 5 into epsilon naught is 8.854 into 10 to the power of minus 12. So we'll get approximately 40. 40 in the sense we can go with 0.44 into 10 to the power of minus minus 10. You will get it, no, 0.44 into 10 to the power of minus 10. That is option B will be the right answer. Okay, I hope you can do this problem. Similarly, move on to the next question. What they are saying to us. Please read this question here. Please read this question carefully. The 2-point charges A and B. 2-point charges A and B having charges plus Q and minus Q respectively are placed at a certain distance apart. And the force acting between them is already it is completed. Please practice by yourself. Please practice. It is repeated in the last video. I hope you can do this. Then you should get it as option C. Please practice this problem because I have explained this problem in the last lecture, the last chapter. Yes, let's see the next one. Let's see the next question. What they are saying to us. Please observe this. Two parallel infinite line charges with linear charge densities plus lambda coulomb per meter minus lambda coulomb per meter are placed at a distance of 2r in free space. What is the electric field midway between the two line charges? Well, let's see here. This is a one line charge and this is another line charge. This is having plus lambda and this is having minus lambda. The separation between the two lines is equals to 2r. Is it clear? Therefore, what is the field at the midway? This capital R and this also equals to capital R. Let us set the point 2. So whenever we consider this point between the midway between the two line charges, due to this positive line charge, the field will be acting towards the right side, and due to this negative also, the field will be acting towards right side. Therefore, the net field at the point O is equals to E due to plus E due to minus. So lambda divided by 2 pi epsilon naught into r, okay, plus lambda divided by 2 pi epsilon naught into r. Don't take negative sign here. Why you should not take negative sign? Because of negative sign only we are getting the directions of this electric field, field. So whenever we do this, then you should get the answer as 2 into lambda divided by 2 pi epsilon naught into capital R. So for simplification purpose, multiply by 2 and divide it by 2. Then you will get 4. You will get, okay, no worries, because all the options are in lambda and pi epsilon naught only. So whenever we do this, 2 will get cancelled. Then you will get the answer as lambda divided by pi epsilon naught into capital R. Capital R. Hence we can go with the option D as the right answer. Option D as the right answer. Okay, I hope you understood this problem. So similarly, move on to the next question. What they are saying to us. Please read this question here. Two metal spheres, one of radius capital R and the other of radius 2R respectively, have the same surface charge density sigma. They are brought in contact. And separated. What will be the new surface charge densities on them? On them? So please think and solve this problem. This problem can be solved in two ways. Okay, let us solve this problem by using a shortcut, So let us say there are two metallic spheres. What is the Q1 value here? Q1 value is, we can say, sigma into 4 pi r square, and Q2 is equals to sigma into 4 pi 2r square, 2r square. Is it clear? Therefore, what is the total charge? Total charge is Q1 plus Q2, then it becomes equals to 5 times 5 sigma into 4 pi capital R square. Let's say it is capital Q. So what is the new surface charge densities? Let's say okay. Whenever the two spheres when when the two spheres are brought in contact when the two spheres are brought in contact, we can say they will share their charges. Therefore we can say, what is the new charge on the first sphere? It can be written as q into r1 divided by r1 plus r2. I have given this and have proved this as a shortcut formula. If you want, you can go and you can check it here. What is capital Q here? 5 into sigma into 4 pi capital R square. What is R1? R1 is capital R and R2 is equals to 2R. Therefore, R plus 2R, it is 3R. We will get it. So R will get cancelled. Then you will get 5 sigma into 4 pi capital R square divided by 3. Now what can I say with the Q2 dash? My Q2 dash is Q into R2 divided by R1 plus R2. So 5 sigma into 4 pi capital R square into 2R divided by 3R. So R will get cancelled here. Then it becomes equals to 2 into 5 sigma into 4 pi r square divided by 3. So they are asking us to calculate what is the ratio, what is sigma 1 and sigma 2. Therefore, what is sigma 1? Sigma 1 is equals to q1 dash divided by 4 pi r1 square. What is this q1 dash value? So just substitute the value of q1 dash here, then you will get it. So observe this, 1 divided by 4 pi r1 is nothing but r square, here r square, into what is q1 dash value? 5 sigma by 3 into 4 pi capital R square. So whenever we do simplification, sigma 1 is equals to 5 sigma by 3. We will get it, 5 sigma by 3. So okay, let it be. And what again is the sigma 2 value here? We can say q2 dash divided by 4 pi into 2r whole square we can write. So what is this? 1 by 4 into 4 pi r square into what is q2 dash. Q2 dash becomes equals to 2 into 5 sigma, 2 into 5 sigma, 2 into 5 sigma into 4 pi capital R square divided by 3, divided by 3. Okay, so just do simplification, then you will get the answer. 4 pi R square, 4 pi R square will get cancelled. So 2, 1, 2, 2, then it becomes 5 sigma divided by 3 into 2, which is equal to 6. So whenever we go with the options, then we can select option D as a right answer. Option D as a right answer. Okay, I hope it is clear to you. Similarly, move on to the next question. I hope it is clear to you, students. So move on to the next question. What they are saying to us. Please read this question. Two identical capacitors C1 and C2 of equal capacitance are connected shown in the figure. Terminals A and B of the key K, are connected to charge capacitor C1 using battery of EMF V volt. Now disconnecting A and B, the terminals B and C are connected. Due to this, what will be the percentage loss of energy? What will be the percentage loss of energy? Okay, so how can they are asking percentage loss? That means you can say delta U divided by U1 into 100%, into 100%. So how can we do this? What is U1 value? U1 value is half C into V square, and delta U is equals to half into C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. So V2 is equals to 0. V2 is equals to 0. So whenever we do this, delta U becomes equals to half into C square divided by 2C into what is V1? V1 is V square. V2 is equal to 0. So whenever we do simplification, C1 will get cancelled. So whenever we do this, we will get delta U becomes equals to 1 by 4 into CV square, 1 by 4 into CV square. So just go with the delta U divided by U1. So therefore, delta U divided by U1 into 100% is equals to what is delta U value here? 1 by 4 into CV square. 1 by 4 into CV square. U1 is half CV square into 100%. So whenever we do simplification here, we will be remaining with only 1 by 2 into 100%. So please do this. If 0.5 into 100%, it becomes equals to 50% of energy will be lost. Hence, we can go with option C as a right answer. Option C as a right answer. Okay. I hope you understood this question clearly. Now, similarly, move on to the next one. Let us see the next question. What they have given to us. Okay. Please read this question here. A capacitor is charged by a battery. The battery is removed and another identical uncharged capacitor. Uncharged capacitor is in the sense V2 should be taken as 0. Connected in parallel, the total electrostatic energy of the resulting system. They are asking here. So let us see. Initially, we can say half CV square is the energy stored in one capacitor. This is the first case. In the second case, what is the potential due to common here? C1 V1 plus C2 V2 divided by C1 plus C1 plus C2. Okay, C2 V2 is equal to 0. We can say that C into V divided by 2C. You'll get V by 2. So what is the C equivalent value? C equivalent is 2C. Therefore, U2 becomes equals to half into C equivalent into V common square. So half into what is C equivalent here? 2C into V common. V common is V square divided by 4. So whenever we do simplification here, U2 becomes equals to we can say half into half CV square, which is nothing but U1 divided by 2. That means it is decreased by the factor 2. It is decreases by a factor 2. Decreases by a factor 2. Okay. I hope it is clear to you. So like that, we have to answer such type of questions, similar type. So like this, we have to think and we have to answer the questions. Let us see. Okay. These are all the questions. These are all the questions which have considered to explain this particular chapter, the electrostatic potential and capacitance. I hope you understood each and every point. So please practice. Please practice as many questions as possible by taking one reference book. Okay, so with this I am going to end today's lecture and today's video, and we'll meet you in the next video. Until then, please keep preparing, don't waste your time. Okay, so thank you very much. Bye bye.